So throughout this chapter, we've been looking at each of the parts of our molecular partition function. We first look at the translational partition function, then the electronic partition function, then we would then have the vibrational partition function, and then we just looked at the rotational partition function. And if we want to look at the total partition function, we have to add all these things. We have to put all these things together. So Q total for our molecule, specifically here, a diatomic ideal gas, is equal to, just multiply all of them together, 2 pi m kBt over h squared raised to the 3/2 power times v. That's our translational partition function. The electronic partition function is assuming that our excited electronic states are not low-lying. It's just whatever is the degeneracy of the ground electronic state. So G for the ground electronic state. Our vibrational partition function is e to the minus theta vibe over 2t divided by 1 minus e to the minus theta vibe over t. Those are vibrational partition function. And then our rotational partition function we just found is t over theta rot times sigma. All right, and so this is our total partition function for a diatomic molecule. We can find this for larger molecules, but just expands the complexity. Makes no difference for the translational and electronic partition functions. Those don't change, but it's the vibration and rotation change significantly because the energy levels change for vibrations and rotations when you're not looking at diatomics. Okay, and that lets us find our total partition function. And then if we want to find, say, for a whole system of molecules that are all the same, of these diatomic molecules, we want big Q. We put it back into this expression that we looked at in the last chapter, Q to the n over n factorial. And that lets us find our system partition function. So we just plug in, literally just what we have here. Big Q for our system is all these things, 2 pi m kBt over h squared raised to the 3/2 times v times g electronic for the ground state times our e to the minus theta vibe over 2t divided by 1 minus e to the minus theta vibe over t times t over theta rotation times sigma, all that raised to the n power. Let me just move this over a little bit so I can do that better. Divided by n factorial. And that is our system partition function. So the interesting thing here, of course, is that everything we need to calculate this are things we can find out from the parameters of the molecule. For example, for the translational partition function, what we need to know is the temperature as well as the mass of the single molecule. Those are the things that matter. Everything else is just a constant. As well as the temperature. For the our electronic partition function, we just need to know what are the electronic levels and are there any low-lying ones and what's the degeneracy. For the vibrational partition function, it depends on the vibrational frequency that shows up in the vibrational temperature that's here. And same for the rotational partition function. It depends on what's the value of the rotational constant, which is dependent on the bond length and the mass of the molecule. So from those parameters that relate to individual molecules, we can build up this entire partition function for the whole system. And then we can go ahead and find, from this, we can find what is our average, whoops, go away please. What is our average energy for our system? Say we wanted to look at a whole mole of a particular molecule, we can then use kBt squared d log big Q dt, holding n and v constant. And so we can do this. We can do this for this equation that we have, right? So this is going to be equal to, right, we can look at log Q and say, okay, this is n times natural log of little q that we have above, minus log of n factorial. Again, that's just a constant. We've seen this before. And so we can say that this is equal to n times kb t squared d log little q dt, holding n and v constant. And then we can find, what's our natural log of q. We can look at just the terms that have temperature. So here that's going to be, we're going to have a temperature raised to the 3/2. They're going to have temperatures in our vibrational partition functions and a temperature here in our rotational partition function. But we can separate all of those out. And look at log little q and write all just the terms that have temperature in them. We'll have 3/2 log t. That comes from the translational partition function. Plus we'll have a log t that comes from the rotational partition function. I'm writing this a little bit out of order, just following my notes here. Then we'll have our theta vib over 2t that comes from the vibrational, minus the natural log of 1 minus e to the minus theta vib over t, and then all the other terms that don't have any temperature component to them. And then we can take the derivative here. So d log little q dt, holding everything else constant. So in this case, we'll hold v constant, as well as n is equal to 3 over 2t plus 1 over t plus theta vib over 2t squared plus, and this one we've looked at before, theta vib t over t squared times this e to the minus theta vib over t divided by 1 minus e to the minus theta vib over t. We looked at that derivative when we did the when we were looking at the vibrational partition function. So then if we multiply by kbt squared, n kbt squared, and we're multiplying again by n kbt squared because that's in our original expression up here, to get to the average energy, we get 3/2 kbt plus kbt. Again, this is translational, rotational energy, plus theta vib over 2 kb. This is 0-point vibrational energy. Plus kb times theta vib e to the minus theta vib over t divided by 1 minus e to the minus theta vib over t. And all of this will just be multiplied by the number of molecules that we have. So from the information about a single molecule, we can link the link information about that single molecule to macroscopic average energy quantities, and pressure and other things. So this isn't the only equation that we can use Q to find thermodynamic quantities. There are also equations for things like entropy and ways to calculate enthalpy, Gibbs free energy, and things like that. But this is just an introduction, so we're not going to go into all those details. But this is of course our vibrational energy. But this is our brief introduction to statistical thermodynamics and how we can link the properties of the microscopic, the individual molecules, to the macroscopic quantities like average energy. So I hope this has been helpful and instructive, and that concludes this video.